We see labels like 100% pure on grocery store items every day. Pure milk, pure ghee, pure juice. To a shopper, that word usually means the product hasn't been adulterated. But to a scientist, that glass of milk is actually a complex mixture of water, fats, and proteins. The scientific definition of purity is much stricter. It requires a substance to consist of only a single type of constituent particle. Every part must share the exact same chemical nature. To understand how matter is structured, we have to look past the marketing definition and recognize that most of the world exists as a collision of different pure components. Before we can categorize these components, we have to identify the two distinct ways they can transform. The first is a physical change. This is when the state or shape of a substance alters, like water freezing into ice, while its chemical identity remains exactly the same. The second is a chemical change. This causes one substance to react with another, changing its composition to create entirely new materials with different properties. This mechanism of change dictates whether materials are simply mingling in a temporary mixture or permanently locking together to form the substances that make up our environment. At the base layer of matter, we find elements. In 1661, Robert Boyle was the first to use this term for substances that cannot be broken down into anything simpler by a chemical reaction. When two or more elements are chemically combined in fixed proportions, they form a compound. If you stir iron and sulfur powder together, they remain a mixture. A magnet can still pull the iron out because the elements haven't changed their fundamental properties. But if you heat that mixture until it is red hot, a chemical reaction occurs. The iron and sulfur bind into a compound with a different color and texture, and it no longer reacts to the magnet. This shows that scientific purity is a fixed, specific state. It provides the consistent building blocks for the various mixtures we see every day. Most matter we interact with, from seawater to soil, is actually a physical mixture of those pure substances. In a solution, the particles break down to a scale smaller than 1 nanometer, making the mixture look uniform. The amount of solute determines its concentration. If you keep adding material until no more can dissolve, you have reached saturation. In a suspension, the particles are much larger and visible to the naked eye. Because they don't dissolve, these particles remain suspended in the medium until they eventually settle to the bottom. Then there are colloids. While a glass of milk looks like a uniform liquid, it is actually a heterogeneous mixture where microscopic particles are permanently dispersed throughout the water. Whether a mixture appears perfectly clear or cloudy like a colloid, or completely muddy, it depends primarily on the physical size of the particles inside. Since colloids and solutions can both appear uniform to the eye, scientists use light to tell them apart. Particles in a solution are too small to interfere with light, but colloidal particles are large enough to scatter the beam. When a beam of light becomes visible as it passes through a mixture, it's known as the Tyndall effect. You can see this happening when sunlight passes through the mist in a dense forest. The tiny water droplets act as colloidal particles dispersed in the air, scattering the sunlight into visible shafts. Light acts as a tool that reveals the hidden physical structure of the matter around us. This flowchart organizes matter into a single structural framework. Everything we've discussed falls into either pure substances, elements and compounds, or mixtures. By applying specific tests, like checking for filtration residue, observing settling, or looking for light scattering, we categorize any material into the system. The world is built from these specific physical combinations: elements dissolving into solutions, particles suspended in colloids, and compounds bonded in fixed proportions.